let us recap what we did in the last lecture. Basically, that in the last lecture it was just very elementary stuff where we discussed what a dynamical system is, and we noted that there could be two different ways in which dynamical systems are specified, either by differential equations or by iterative maps. If it's a differential equation, we write down the derivative of variables dx by dt, dy by dt and so on, and in one dimension there is only a single variable. So, we had x dot was specified by some function f of x. If it was an iterative map, on the other hand, given the state of the system at time n, that is x of n, we had a rule for going to the next time instant, namely x at the time n plus 1, and that was given by some functional mapping. Now, what we discussed was that we had these systems specified by the number of variables. Here it is just one dimension. The evolution equations were given in one of these two forms, and then we needed to analyze the system in a mixture of both qualitative and quantitative methods. In order to first figure out what the important features of this system were, we noted that it is important to identify stationary points or fixed points of the system. Stationary points are those points where essentially nothing happens. So, if x dot is equal to 0, the velocity is 0, then the system will not move. And this happens when the right hand side of the equation f of x was equal to 0, and f of x being some function takes a value 0 at one or more points, which we just denote by x star. In the case of iterative mappings, nothing happens when x n is equal to x n plus 1, namely it is a fixed point, and this will happen if f of x n is equal to x n, and that means that we need to solve an equation f of x is equal to x. That gives us one set of roots which are termed x star over here. So, the equations are slightly different, but not really different in principle. Now, these fixed points are stable in the following situation. If you have the differential equation, namely x dot is equal to f of x, then the fixed point is termed stable if the derivative of f at the point x star is negative, and if it is if the derivative is positive, then the fixed point is unstable. For the map, on the other hand, at the fixed point, if the derivative is less than 1 in modulus, then the fixed point is stable, and if the derivative is greater than 1 in modulus, the fixed point will be unstable. So, this more or less summarizes what we had discussed in the previous lecture, and let me just point out that in general, in one dimension, these are the only possible behaviors, namely you can have fixed points. Of course, you can have no fixed points at all in some exceptional situations, but if you have a fixed point, then the only possible behaviors are that it is either stable or unstable. Of course, there is this intermediate case of being neutral, but those are not particularly interesting, and I am not going to spend time discussing them. An important geometric point over here is that when there are several fixed points, because we are considering the situation in one dimension, if I have a stable point, let me call that over there, and if I have an unstable point over here, if I have another point over here, it has to be stable. You cannot have a situation where you have two unstable points, one next to another, because as we saw in the previous lecture, the vector field points away from the unstable point, it points away from this unstable point. So, somewhere in between there must be a point which is stable, because the flow is coming in on both sides. So, we must always have alternation between stable and unstable fixed points. Now, this is what happens in one dimension. There is a lot more to be said, and we will come back and talk about one-dimensional systems in great detail next week. But when there are more variables to be considered, namely in higher dimensions, the behavior is somewhat more complicated, and we will turn to that shortly. Before I turn to that though, let me point out that for this course I have already specified that we will be largely following these books. Beautiful book on nonlinear dynamics is by Stephen Strogatz, and that is the title over there. There is an edition available over here. There is a very nice slender little book on mathematics by Holmgren, which is titled A First Course in Discrete Dynamical Systems. And then of course there is the classic book by Ed Ott, Chaos in Dynamical Systems, and there are several editions of this book. I should point out that this is an introductory course, and almost any textbook with the words nonlinear dynamics or chaos in the title particularly will have a lot of material to offer, and any book can be followed, so to speak. They are not going to be at variance with one another. Where they will differ really is in the order in which the topics are presented, but the material is the same, and there is a huge amount of stuff that is available on the internet, starting with Wikipedia, Scholarpedia. There are any number of sites where people have got material wherein they discuss these concepts of nonlinear dynamics. Okay. Now, in this course, I am going to be going through in a somewhat nonlinear fashion through these various topics, and my personal choice is to try to understand what happens in systems around fixed points. So, in one dimension, as we saw, the fixed points are very simple and can be classified very trivially. In two dimensions, and this is symptomatic of what is going to happen in higher dimensions, the situation is a little more complicated. So, let us start by considering a linear system in two dimensions, and let it be autonomous, that is to say time is not going to appear on the right hand side, and the two variables that I am going to denote for the axes are x1 and x2. This is mostly for notational convenience, and occasionally I will slip into calling it the x-axis or the y-axis, but hopefully you should be able to figure out what I mean by the context. So, the two axes, as I said, are x1 and x2. So, this is the x1 axis and this is the x2 axis, and this linear autonomous flow in two dimensions is just the following set of coupled first order differential equations, linear. Because it is a linear system, I can define a vector. This is the variables x1 and x2, that is my vector u, and if I take the matrix of coefficients a, b, c and d, then I can rewrite this equation as u dot is equal to a times u. That is to say, this equation can be written down as u dot is equal to a u, where these are the two vectors. Oops, sorry, some mistake over there. All right. Now, depending on the values of a, b, c and d, the right hand side of this equation, this gives us a vector field, and that can also be sketched like we saw in the one dimensional case. So, here is an example for A equals 2, B equals 3, C equals -2 and D equals -1. We have the following vector field, namely what we do is to go back to these equations, and at any point x1, x2 you draw the vector in the x1 direction as that, and the vector in the x2 direction as that, and the resulting vector is pointing as it is. And here we see automatically that this fixed point, the fixed point is at the origin 0, 0. This fixed point has an interesting character in the sense of, you can see that there is a circulation around the fixed point, and that is what the flow shows. Now, I drew this particular vector field using this online resource desmos.com, and you can just go in there and enter your equations of motion. That is, you can enter the right hand side in 2 dimensions, and it will give you an image of what the flow is like. All right. If I change A, B, C and D, and for these values of A, B, C and D, the flow is somewhat different, and here you can see that there are arrows pointing inwards along this direction and outwards along this direction. Now, the whole notion of stability therefore needs to be looked at a little more subtly over here in 2 dimensions. The origin is clearly the only fixed point. From these 2 equations, you can see that the only solution which is going to give us both of them equal to 0 is 0, 0. And to determine its stability, we proceed as follows. First, let us carry out a linear transformation to a new basis V, which I will index by the 2 variables y1 and y2. And the transformation between u and v is given by this linear transformation over here, and the matrix B being chosen to diagonalize A. In case A cannot be diagonalized, there is a standard appropriate form in which we would like the matrix B to be. In case A cannot be diagonalized, B can be chosen to bring A into some standard form. But in the simplest case, the matrix A can be diagonalized, and we choose B as the matrix that will diagonalize it in the following way. So, B A B inverse is equal to lambda. Right. Now, if the eigenvalues of the matrix A are lambda 1 and lambda 2, then the matrix, the diagonal matrix lambda is just given by this particular diagonal matrix. And if you just follow the algebra over here, you can clearly see that V dot is equal to lambda times V. Writing this in terms of the variables, you find that y1 is equal to lambda 1 times y1, and y2 dot is lambda 2 y2. That is, by this linear transformation, we have separated the 2 variables and got much simpler equations, which are effectively just one-dimensional equations. Right. Now, we have already done the analysis for one dimension the last time, and therefore, the stability or instability of this particular system is very trivial for us to determine. This is going to be stable if lambda 1 is negative, and unstable if lambda 1 is positive. Likewise, this will be stable if lambda 2 is negative, and unstable if lambda 2 is positive. All right. Now, these eigenvalues are the roots of a quadratic equation, and again, given the fact that this is a 2 by 2 matrix and fairly simple to solve, we can see that the quadratic equation which you need to solve is just lambda squared minus tau times lambda plus delta, where tau is the trace or the sum of the diagonal elements. Okay, recall that the matrix A is A, B, C and D. All right. So, the sum of the diagonal elements is the trace and the determinant is delta, and the eigenvalues are given by the following equation. And now, I mean, the difference from one dimension begins to be seen over here, because depending on the values of tau and delta, which of course depend on the matrix elements themselves, there can be several possible cases. To start with, if tau squared is greater than 4 delta, then the discriminant is positive. The square root will give us 2 real numbers, and depending on various possibilities, we can either have both the eigenvalues as positive and real. You can have both the eigenvalues as negative and real, and in one case you can have one of them positive and one of them negative. These 3 cases, and I will come back to this, are termed unstable node, saddle node and stable node. The node refers to the fact that 0 is the fixed point, and the stable or unstable tells you, stable or unstable, or the saddle tells you what is the behavior in the neighborhood of the node. Now, since the solutions that we have in this particular case, the equation itself is a trivial one-dimensional equation, and the solution is y sub I is equal to y sub I of 0, that is the initial value of y sub I, times e to the lambda I times t. If either of the lambda i's are positive, then the dynamics will eventually diverge, because then you will have a function that grows in time. So, if either of the lambda I are positive, then the dynamics will eventually diverge, and the fixed points must be classified as unstable, because any motion in the neighborhood of the fixed point will eventually go away. Now, the x sub i's are related to the y sub i's by a simple linear transformation, and therefore, if it is unstable in the variables written down in the y coordinate system, it is going to be unstable in the x coordinate system as well. Now, when tau squared is less than 4 delta, then both the eigenvalues are complex, and writing them as lambda 1 is alpha plus I omega and lambda 2 is alpha minus I omega, one can see that the solutions are going to be of the form e to the alpha e to the plus or minus I omega. Now, these have to be taken in suitable linear combinations to give real solutions, because after all the solutions of the equations are real, and therefore, these combinations that are going to give us real solutions out of e to the I omega t have to be trigonometric functions, sine and cosine omega t, and these are being multiplied by e to the alpha t. So, we have an exponential times an oscillatory term, all right. So, basically we find solutions that are going to oscillate in time, but the amplitude can be variable. Now, since the motion is in the plane x1, x2 or y1, y2, the motion will circulate about the origin with a time dependent amplitude which depends on the alpha. One again has 3 possibilities: alpha positive, in which case it is spiraling outwards because it is moving, the amplitude, if this is the fixed point, things are moving outwards. If alpha is negative, then around the fixed point we have stuff that is moving inwards, and if alpha is equal to 0, then it neither grows nor shrinks, and we have what is called a center. In this previous case of the stable and unstable or saddle nodes, in the case of the unstable node, the in the y1 direction it is increasing, in the y2 direction it is also moving away, and so this is the kind of behavior which goes with it being an unstable node. In the case of both negative eigenvalues, we have a situation where the motion is coming inwards in the y1 direction and it is coming inwards in the y2 direction as well. The interesting case over here is of the is the case where you have one positive and one negative eigenvalue, and that gives us the following, that in the y1 direction the motion is moving outwards because lambda 1 is positive, and in the y2 direction lambda 2 is negative. So, things are moving inwards, and this is the reason why it is called a saddle, because you have one direction which is moving outwards and one direction which is moving inwards, sort of like the saddle on which one sits on a horse. Okay. So, given this particular scenario, depending on the value of tau and delta, we can have not 2 but 6 different behaviors, and these 6 can be separated out as, this is of course unstable. The saddle has one unstable direction and therefore it is just unstable. The stable node is stable, all right. And here we have the unstable, which is a spiral, which would be classified as unstable obviously. The stable spiral is one of the stable ones, and the center is also stable in the sense that it is not unstable. So, out of the 6 types of fixed points or the 6 types of stationary points that we can have in a two-dimensional case, these can be represented in the following way. There are 3 of them which are stable and 3 of them which are unstable, and they occur as follows. Here is a sort of a phase diagram, if you like, of the system as a function of tau and delta. The line tau squared equals 4 delta, that particular line is this parabola over here, and that separates the real from the complex eigenvalues. In the real case, if tau, for positive tau and below this particular line, we have both the eigenvalues positive. On this side, you have both the eigenvalues negative, and therefore you have the stable node on one side and the unstable nodes on the other side. And below this line, okay, so for all negative delta, you have saddle points. Within this parabolic region, along the line tau is equal to 0, you have centers, because to have a center, there is the real part of it must be 0. And you can see that the real part of the eigenvalue, is always tau. So, if tau is equal to 0, we have a center, and if delta is positive, then you have the complex, the purely imaginary roots. And on this side you have the unstable spiral, and on this side you have the stable spiral. Along the line, you have a transition from the unstable spiral to the unstable node, and on this particular line tau squared is equal to 4 delta. Occasionally you will have exceptional behavior. These are the degenerate stable nodes and the degenerate unstable nodes. In the same way, of course, being on this line tau is equal to 0 is also exceptional. So, in a sense, centers are also exceptional behavior. All right. So, this summarizes what we know about fixed points in 2 dimensions, and they can be of these 6 following types, but this is purely for the linear system. How does this analysis move on when we have nonlinear systems. When you have this general dynamical system which is nonlinear, the right hand side is specified by a function some f1 of x1 x2 and f2 of x1 and x2, and these are different velocity functions, and they will depend on x1 and x2 in maybe complicated ways. The analysis, however, proceeds in the same way as we did in the one-dimensional case, where we considered nonlinear velocity functions. It's important to locate stationary points, and it's important for the following reason, that in the vicinity of such equilibria, the system can be linearized, and then we can analyze it in the way in which we have done earlier. So, we start by linearizing in order to find the equilibrium points, we start by setting the right hand side of these equations equal to 0 to find those points where the entire vector field will vanish. When we set f of x1 x2 to 0, and this gives us an equation where the variables x1 and x2 are functionally dependent upon each other, that may specify a curve in the plane. In this particular case, it will be a curve, and this is termed this is called a null-cline, because it has a value which is strictly 0 along this particular curve. Similarly, if you take f2 of x1 and x2 equals 0, this gives us the x2 null-cline, and the points of intersection of the two null-clines will give us the equilibrium points of this system. So, the intersection of the two null-clines will give us the equilibrium points. And here is a very nice example from Strogatz. Okay, it's one of many possible examples, but if you have access to the book on page 147, the following rather simple system is given. X1 dot is a function of x1 and x2, which is x1 plus exponential of minus x2. x2 dot is minus of x2. So, the x2 null-cline, simple enough, is just the x1 axis, because it says x2 is equal to 0. The x1 null-cline is this curve. From here you can figure out x2 in terms of x1 is just minus the logarithm of minus x1. Therefore, this curve is not defined in the positive x1 on the positive part of the axis, and you can draw it rather simply over here. So, that is your x1 null-cline, and here is the x2 null-cline, which is just the the x1 axis, and the intersection of these two curves, that point gives us the equilibrium point for this system. What is the advantage of the equilibrium point? Now, in the neighborhood of the equilibrium point, since f1 of x1 x2 star and f2 of x1 star x2 star are both equal to 0, you can take a Taylor expansion and try to see what the differential equation that we were considering, this differential equation, how does this transform under or how does one linearize around this particular fixed point. So, this is fairly straightforward. I look at small displacements from x1 star, let me call that delta x1, and a small displacement from x2 star, call that delta 2, and to leading order now, since x1 and x2 star are just points, they do not have derivatives. So, to leading order we get d by dt of delta x1 is approximately f of x1 star x2 star plus delta x1 times the partial of f1 with respect to x1 and delta x2 partial of f1 with respect to x2, and of course, there are other terms further on. Similar equation holds for delta x2. these partial derivatives, okay, from Taylor's theorem, they have to be evaluated at this fixed point x1 star x2 star. Now, simplifying notation, noticing that both these terms are going to be 0 and the delta is of course superfluous in this notation. So, we get the linearized equation around this fixed point as d by dt of x1 x2 as this matrix of partial derivatives, and this matrix of partial derivatives multiplying the vector x1 x2, or even further simplifying our notation, writing Fij as partial of F1 with respect to partial of xj. So, Fij is partial of Fi with xj evaluated at the fixed point. We can rewrite this entire equation compactly as d by dt of x1 x2 as f11 f12 f21 f22 of x1 x2. Notice that this is exactly our linear equation in 2 dimensions that we started today's lecture with. In the previous example, the fixed point was at -1 and 0, and the linearized equation around that point is obviously given by dx1 x2 is, and here is the matrix of partial derivatives to be evaluated at the fixed point. So, the derivatives are just 1 minus e to the minus x2, 0 and minus 1. Putting the value of the fixed point as -1 and 0, you get this very simple matrix. Now, the eigenvalues of this matrix of derivatives, which is termed the Jacobian, they are plus and minus 1, and one of them is positive, one of them is negative. Therefore, the fixed point is a saddle. The null lines give the curves along which the velocities vanish, and thus we can see in this example that the eigenvalue -1 is associated with the x1 null line, which is the stable direction, and the eigenvalue +1 is associated with the x2 null line, which is the unstable direction, and this is what the flow looks like. So, expanding it a little over here, you can see that here is the fixed point, this is the variable x1 and this is x2, here is the point -1 0, and this is the unstable direction and this is the stable direction, and this is obviously a saddle. Okay. In the linear system, the saddle would have just been a set of straight lines with one unstable direction and one stable direction. Because the system is nonlinear, we can see that this this stable direction actually curves, and the further you go away from the fixed point, the further the region of linearization is such, the further you go away from that place where the linearization is a good approximation, you are going to be able to see the curvature in this in the null lines. Now, this image is taken from Strogatz's book, and it shows the vector field, the nonlinear saddle, and in addition to the vector fields, which are these arrows that you see over here, and the nonlinear saddle, you also see some examples of phase curves, namely what would happen if I started at a particular point and moved on and integrated the equations of motion. Now, these phase curves are representative trajectories on the phase plane in this two-dimensional system. It is interesting to note, and you can verify it for yourself, that the phase curves are always tangent to the vector field. Okay. I have already pointed out that linearization is only valid in the neighborhood of the fixed point, and further away from the fixed point these the linear approximation will break down and the lines could become nonlinear. Nevertheless, there is an important point to remember, that it's only at these stationary points that this behavior, which is describable, can change in any drastic manner. The vector field itself can only change smoothly and gradually as you move outwards, and any abrupt change in motion will require additional stationary points. A point that I should note is that phase curves that start out with different initial conditions cannot intersect in any number of dimensions. So, if I start with a point over here and I move on this particular curve, if I start with a point over here and move along this particular curve, I start with another point, this behavior is not possible. So, through any point in the phase space, there is one and only one trajectory. Okay. So, to summarize, in this lecture we have examined two-dimensional systems in some detail. We have looked at flows, and we have seen that there can be several kinds of fixed points. In the neighborhood of the fixed points, the system can be linearized, and there it has one of the 6 standard behaviors. I have already pointed out that there can be some other cases which are the marginal ones. These are exceptional and are discussed in the suggested books. Away from the fixed points, the nonlinearity becomes more pronounced, but the vector fields themselves will change smoothly. In the general case, orbits are usually computed numerically. Most systems cannot be integrated analytically, and as the number of dimensions increase, this will get progressively more and more difficult. For this course, it will be essential, in order to do any of the homeworks, that you should be able to carry out computations. And although there are some tools available on the web that allow for numerical exploration without programming skills, these are limited. So, you would be well advised to pick up any one computing language. That is about it for today. Thank you.